So my name is Ludovic Cortés. I'm from INRIA, a research institute in France in computer science and math. I'm also the co-maintainer of GNU Guix. So this piece of software that I'm going to talk about, it's actually pronounced Guix, which I think is quite unusual to many, but yeah, that's the way it is. Last year, I already had the pleasure to talk in the HPC dev room together with Piotr Prince. We gave a general overview about Guix, and Piotr talked about relocatable binaries precisely for HPC. This year, I want to talk about a bit of a more prospective thing that we'd like to work on, that we are already working on, but we'd like to make more progress in that direction. And this is about integrating deployment tools within scientific workflows. Just a quick show of hands before I start. How many of you are already familiar with Guix? That's like half of the room, I would say. Cool. Okay, I'll do a quick introduction to Guix so you get a feel of what it's like, what it does, and what makes it different from other tools. For those of you, at least, who did not attend Kenneth's talk this morning, which I think did a great job at showing all these different tools. So in a nutshell, Guix is essentially a package manager. I suppose most of you have already used CounterSpark or APT or that kind of stuff. So it gives you essentially that kind of interface, like apt, like counter install, that stuff. So you have a command which allows you to install packages, GCC, OpenMPI, HWlog, for instance. Then you have this command which is a little bit particular because it has module-like functionality, right? So if you use to module load, well, this is kind of similar. So Guix package -- search path give you the list of environment variables that you need to define to actually use the software you installed, essentially. So you can just add that to your shell and you have all the environments ready to use. I think that's pretty convenient. I mean, it's always tripped me up before that I forgot to set this or that environment variable, so I really like this. Then you have another way to install packages, which is that instead of having the usual apt style command line interface like this, you can say, well, I want to declare precisely what I have, what software I have available in my profile. So I just write a simple file that contains a list of packages I want to have, and I pass that file to Guix package -- manifest, and it just creates the profile with all these pieces of software. That can be quite convenient if you're moving between different machines, like you have a set of packages on your laptop and you'd like to have the exact same set on your supercomputer. Well, you can just put that file on and just, do Guix package -- manifest. And we have transactional upgrades and rollbacks. So, you can try out new packages, new versions, and if it doesn't work and you have a paper due to, for tomorrow, well, you can still roll back. And that's fine. You have the exact same tools as you had just before upgrading. So this is essentially the main interface to Guix, I would say. The cool thing about it is that it's reproducible. So what do I mean exactly by reproducible? Well, let's say you have somebody on their laptop using Guix to install some set of packages. Well, then you can have somebody else on a completely different GNU Linux machine, so it's GNU Linux only. And as long as that person is using the same commit of Guix, they're going to be able to install the exact same programs, the exact same packages. And by exact same, I mean at the bit level. So the Guix project is actually involved also with the reproducible builds effort, along with Debian, Arch Linux, FreeBSD, lots of distributions. And so we pay a lot of attention to making sure that we have bit reproducible builds. I think that's a key difference to some of the other tools out there. So yes, that's reproducible and portable. So again, you can, you have your cluster, your supercomputer, which has a completely different distribution than your laptop, but that's fine. Guix is self-contained, so it will always create, its own set of packages, and, it's independent of what the whole distribution provides. I should mention also that Guix does, like Nix and like Spack is doing now, does mixed source binary deployment. So if you have binaries available, which we usually do, well, then you just end up downloading those binaries, and if you don't, then you just build from source, and it's completely transparent. So we have this reproducible thing that you can replicate from one machine to another. That's bit reproducibility. But I think in science in general, we want to be able to do more than just replicate bit by bit the software environment. Sometimes you want to experiment, and that's one thing that SPAC does really well. If you saw Todd's talk just before, I mean, there are lots of options you can add to SPAC to specify, like how you want to build your package, what dependencies you want to use, and that's definitely useful in an HPC context where people want to try out things. So with Guix, we offer some flexibility at the command line. Like you can say, so there is, for instance, a package for HWlog, the hardware topology library, in Guix proper, and it's a fixed package, right? It's a given version, it uses given configuration flags and so on. But as a command line, you can say, actually that's a real use case, because some of my colleagues work on HWlog, and sometimes they want to try out release candidates, and this is something for them, I guess. You can always say, I want to build HWlog, but I want to use a different source table. So you can provide a file or a URL. It's going to use the same HWlog package recipe that's available in Guix proper, except that it's going to use this source file. That can be quite convenient. And you can also say, well, I like that mums solver package in Guix, except that, I like to use different dependencies. Like I'd like to use the parallel version of Scotch, the graph partitioner. Well, you can just say, okay, I want to, take that mums package, but I want to rewrite the dependency graph such that any reference to the Scotch package is replaced by a reference to the PT Scotch, parallel Scotch package. And that's going to do that on the fly. And so probably you will end up building from source because the build servers don't have this particular set of binaries. But I mean, you get the flexibility that many people need in HPC. And again, this example is, I guess we owe it to Kenneth. The discussion about binary performance. For some pieces of software, you need to choose at compilation time whether you want to build a generic version of the software or whether you want to build an AVX, for instance, optimized version. And this is how you could address this kind of situation where, Guix itself provides a generic version that works on any x86-64 machine, for instance. But if you want the AVX version, you can always say, okay, rewrite the dependency graph so that I use the AVX variant of FFTW. So Guix started in 2012. It has almost 7,000 packages currently. It builds on a number of architecture. We got AArch64 recently. And we have a continuous integration build farm that provides binaries at this URL. The last release was in December last year. I think we could be doing a better job at making frequent releases. We're working on it. But we had like two releases last year, I think. And the new thing compared to last year is this Guix HPC effort. Essentially, we realized that some of us in the Guix community, so Guix is not initially designed for HPC at all. Well, I mean, not specifically. But it has good properties for HPC, like the fact that you can install packages as a user without being root, and you have a lot of flexibility, and every user can decide what packages they install. This kind of property is quite useful in a cluster, typically. So we realized that actually several of us in the Guix community were already doing HPC stuff and using Guix in that context. So we created that Guix HPC effort. Initially started by INRIA, the Max Delbrück Center for Biomolecular Medicine in Berlin, and the Utrecht Bioinformatics Center, also joined by people from Cray. So we're trying to see what else can be done to make Guix a good choice for package deployment in HPC. So we've already made a number of improvements in that area, and we hope to do more. And so this is an invitation for you to join us. If you're curious about Guix and you'd like to see if it would fit your use cases, Or if you, I don't know, if you'd like to chat in general, well, we welcome you to join us to have a look at that website here. And yeah, hopefully we can talk and do stuff together. Right, so I don't know if you had the opportunity to go to the Unix history keynote yesterday. I think it was pretty cool, pretty interesting. And Unix has this well-known motto of having one tool for a job, one tool that does one job and does it right. I think we all like it. In general, as a concept, it's a pretty good idea because it means that you have to create tools that can be composed together, right? And the general idea is sound. I mean, it makes a lot of sense to me. Yet in Unix, composition of programs is a bit limited. Like, essentially, you can share text through pipes or through files, stuff like that. And so you can compose things like cat and WC, stuff like that. That works well. But if you're trying to compose other pieces of software, sometimes it doesn't work so well because you want to share higher level concepts, not just strings of text. And I think this is what led us to what I call the archipelago of tools that do one thing. So we can see that in HPC on clusters, I think. We have tools like, let's say we have APT here, which is a tool that is used to deploy software on the main distro. And then somewhere we have, I don't know, EasyBuild Conda, which is a tool that users or sysadmins actually use to deploy more software. And then somewhere around there we have the batch scheduler, which simply ignores the whole issue of software deployment. And then again we have CWL or Galaxy, for instance, which are tools to run pipeline workflows. And again, they mostly ignore the issue of software deployment. I think that's a problem. I think we could do a better job if all these tools, these different tools, could be made aware of software deployment. Right? This is what we're trying to achieve with Guix, actually. We're trying to put reproducible deployment at the center of the stage and to provide tools that can be used to build applications around the notion of package and software deployment. So let me give a couple of examples. So as I said before, Guix it initially started as a generic package management tool, right? So you can install software. But since Guix knows all this dependency graph of packages, we can actually create other applications around it to make use of that information. So let's say, for example, as a developer, one thing we often want to do is be able to say, okay, I fetch the source of the software I want to work on, let's say PET-C, and then I actually want to hack on that piece of software, right? So I need to set up the environment for that software. Well, we have a Guix environment command where you can just say, I want to hack on PET-C, and Guix already knows about PET-C, right? It knows about its dependencies. So you just say Guix environment PET-C, and it spawns a new shell where you have everything available to develop PET-C. I think that's pretty convenient as a developer. It's one case where we're just using information that's already available and just making new tools using it. Container provisioning is another case where we have a disconnect between the main tools that are used to provision containers and package managers, for instance. I think that's wasteful. Because if you're using Docker, so the general approach would be for Docker to use a base image, let's say a Debian image, and from there you have a Docker file that runs a bunch of apt and conda commands, for instance. And it does a job, but it's not reproducible. And it's not, why is there this disconnect? Why can Docker be made aware of, the package graph? I think we can do a better job. And so with this Guixpack command, what we have is a generic tool that again uses information already available in Guix, which is the dependency graph, and is able to create bundles. The bundle itself can be a generic tarball that you can extract on a different machine, or it can be a Docker image. And you can create that Docker image, and here what we end up with is a Docker image that contains HWlog and all of its dependencies. And from there, I can just take that image, pass it to someone who, well, maybe hasn't seen the light yet and is not using Guix, and they can still use that software in using the tools they're familiar with. So I must say I'm a bit of a programming language geek. So I'm trying to do a very weird exercise, which is to talk about functional programming and scheme in an HPC track. I hope that will work. We'll see. I couldn't help but tell you a little bit about the underpinnings in terms of programming language features that we have that make this possible. So let's see. So Guix itself is written in Scheme, which is a functional programming language of the Lisp family. In Scheme, we have expressions. So this is an expression, Scheme expression. As you can guess, it's basically like it simply invokes the ls-topo program, right? So it uses the system star function, which is like the system function in C, roughly. And this is an expression, okay? If we had a quote right here, then what we get is an abstract syntax tree. So it's an unevaluated expression, so to speak, or a stage expression. So I can take this, I can write it to a file, or I can send it over to a different machine. But of course, if I send it over to a different machine and I want to evaluate it there, well, as you can guess, maybe it's not going to work, because this bin ls-topo thing actually means something, right? It refers to software. And the expression here doesn't capture the fact that I'm referring to the ls-topo command of hwlock. So we need something more. And in Guix, we actually extend the programming language with an additional stage notation, which is this hash tilde thing, where here I'm saying, okay, I'm building an expression, but it refers to a specific hwlock package, right? So in other words, we have an expression that is aware of the deployment needs for itself, right? It carries information about what software needs to be deployed for the expression to actually work. And again, this hwlock here, it's actually a reference to a variable, and that variable describes a complete graph, right? This is hwlock. This is what's going to be deployed when I evaluate that expression, let's say, on a remote computer. And so we've put deployment within the language in a way. And when we had that, well, we can start building applications around it. So one of them is a Guix workflow language currently being developed by Roel Jensen of the Utrecht Bioinformatics Center. I don't know where Roel is. It's basically using that feature to make deployment a core part of the workflow language. I don't know if there are bioinformaticians in the room. Yeah? Okay, so I'm not a bioinformatician, right? So I'm trying to explain the whole situation. But basically, in bioinformatics, people run big pipelines, right? They have lots of different tools in lots of different languages, and they compose them to build, analysis of DNA sequences and stuff like that. And they basically have a graph of tasks that need to be performed using all these pieces of software. So basically, as an input, you have data, and then you have this big graph that uses tons of pieces of software, and then as the output, you have, the end result, the computational result. But for each of these boxes, you actually need to deploy software. And in bioinfo, people, the de facto standard is CWL, Common Workflow Language, which is a tool that allows you to describe workflows. So far, so good. But again, it doesn't take care of software deployment by itself. So you are not really able to express the fact that you need not just to run software, but you also need to have that software deployed first. And that's something that GWL, I think, solves in a pretty nice way. So just to give an example, this is a GWL process definition, where essentially we use a bunch of modules that define package objects and workflows, things like that. And then we can define a process where we specify dependencies. And again, when we say Python here, we're referring to the Python package that's defined in this very module. So we're precisely referring to one Python instance. Same for the SAM tools thing. And then we essentially provide, in this case, a Python snippet that does stuff, does computations. From there, we can just run Guix workflow, and it's going to submit the whole set of tasks using, in this case, the SunGrid engine batch scheduler. It's going to submit that on your supercomputer and make sure that everything is deployed and accessible in the compute node. I think that's pretty nice to have this property. Okay, I'm going to wrap up. Now, if we take a step back, in terms of reproducible science, it's becoming more and more of a hot topic. So this is, for instance, Nature insisting that people should be providing code and not just data. This is, I guess, another Nature magazine. Well, and we get the point. The ACM also in computer science is insisting that, well, it's not okay to just have a paper that says that you have code that does great stuff, right? You need to have the code, and people need to have a way to reproduce it. And there are initiatives like the Rescience Journal. There are many others, but this is the one I happen to know best, which essentially seek to reproduce experiments that are described in papers. I think to do that, you first need to have the code of the software involved, and you need to be able to build that software. Which brings me to my conclusion. If we look at the whole reproducible science spectrum, at one end we have initiatives like the Rescience Journal, which is scientists trying to reproduce experiments and to fiddle with experiments. At the other end, we have initiatives like Software Heritage, which protect software source code from disappearing. If we have both, that's already kind of nice for reproducible science. Of course, it takes more than this to make science reproducible, but these are very useful tools. And you see what I'm getting at. We miss something here for deployment. And what if Guix, for example, could be used to make reproducible deployment available so that we could build those ideal reproducible science workflows? And this is it. If you have any questions. Yes.
Why did you decide to create a new workflow language when there are plenty of them? Instead of contributing to the CWL and extend it to install the package. So CWL is based on Docker containers. You could have extended it to make it install Guix instead of creating a new language.
All right. So let me repeat the question. So essentially, why did we create a new workflow language? I think this is actually not my work, but I think the main motivation to create the Guix workflow language is to incorporate deployment within the workflow language. So from my understanding, CWL, for instance, so there are two main ways to use it. Either you just do deployment by yourself, and that's it. CWL doesn't care at all. Or you can use Docker images. And CWL, in a CWL spec, I think you can specify a Docker image. But it's still up to you to actually create that image and deploy it on the nodes and so on and so forth. So, I mean, I can understand your argument, which is that CWL already exists and there are lots of tools. And yeah, that is great. I think we have an opportunity here with GWL to actually make things simpler, right? To have deployment be part of the whole workflow management process. I think that's pretty useful, even though in some cases, yeah, probably people already have their CWL workflows and they're not going to switch overnight, right? Yes?
How's the data managed in GWL? So you skipped over the part of the script what the input files were.
Right.
I guess I'm curious how that works.
So the question is, how is data managed in GWL? So, yeah, we had a discussion about it. So I'm not an expert in terms of design of GWL, but basically the issue was, how should we treat data? Should we put in that store, that GNU store directory that Guix uses? Because it's content address, at least for data. So that was one option, but the problem is that data is typically very large for bioinformaticians, and so they just didn't want to have that bottleneck, which would be the central store. So data is treated out of band from a Guix perspective. So I don't know exactly, maybe we should discuss afterwards, but I think GWL arranges to have data stored outside of the store and just make sure it's available on the compute node. Yes. Yes.
You talked about I knew actually. So you talked about the integration engineering systems that you
Yes.
And just really quick, what did you do? Did you integrate one framework like continuous integration, building when you have other options, for example, build or something that you just focusing on your build system, and so why do you integrate yours?
So the question, if I understand correctly,
so you have a framework that's just doing continuous integration system.
yeah.
For example, build roads, and you integrate in your package, you integrate the opportunity to do integration continuously.
Right. So the question is, why do we have a specific continuous integration tooling? Roughly, did I get that right? Yeah. Well, continuous integration is very important to us because we need to be able to distribute binaries of those packages. So we need to have servers somewhere building packages in advance so that when users actually try to install them, binaries are already available. So that's why we're doing continuous integration, and also obviously for QA. Yeah, I think that's the answer. Yeah. Okay. Thank you.